Okay, we're going to continue our exploration of partial fractions today with exploring what happens when you have repeated or nonlinear factors in the denominator of your rational function. Oh, and I just saw that I'm missing a dx here. All right, so let's start with this first one. This is a good example. First, double check we don't have to do any division because the numerator has a smaller degree than the denominator. And I can factor the denominator by taking out an x. And I get this. And x squared plus 3 does not factor any further. If it was x squared minus 3, you would factor it further as x plus root 3 and x minus root 3. But when it's a sum like that, you can't factor it any further in the real number systems. So let's set up some partial fractions here. I would have... my two denominators are x and x squared plus 3. So x is a linear factor. It's a first degree polynomial. So in the numerator, we just put an a like we've been doing already. But the second one is different. This is not a linear factor. It's quadratic. And so what we kind of don't tell you always when we're doing linear factors is what we're really doing is going 1 degree less. So since this is like x to the first, in the numerator, I do like a 0 degree, which is really just a constant, a. But in x squared, I have to go 1 degree less than that and do a linear factor. So the general approach for partial fractions, whatever the degree is in the denominator, go 1 less in the numerator. For linear ones, that's easy. The numerator is just a constant. But for higher degree denominators that don't factor further, you just go 1 less. All right, so then if I do a little common denominator work, my numerator here would be a times x squared plus 3 and bx plus c times x equals x minus 3. Okay, so then I could distribute my a and distribute this. All right. So then I can see, I'm going to just write a little system of equations. I'm going to write out what the x squared terms are, the x terms are, and the constant terms. So the x squared terms are a plus b equals, there's no x squared term on the right side of this equation, so a plus b is 0. My linear terms, there's only the 1, there's only c, and so c is 1. Well, okay, that makes things easier, doesn't it? And then my constant terms, I've got the 3a, and that's it. And so 3a is negative 3. Now, I think I went over in class today how you could solve this system with a matrix, but this is such an easy system, we don't need that. So a is negative 1, and that means that b is positive 1. Okay? So I can rewrite my integral now as, integral of negative 1 over x plus 1x plus 1 over x squared plus 3. And then we look to see if we can take these integrals relatively easily. The first one, yes, negative natural log of x, no problem. The second one, not so nice. You could do a trig sub, but one technique you can use is you can split this into two fractions, and I'll show you what that does for us. I could write it as x over x squared plus 3 and 1 over x squared plus 3. So this isn't really partial fractions, but it is a calculus trick that makes the integrals a little bit easier. So this one would become negative natural log absolute value of x. And then this one, I see a u du pair, right? If I make u be x squared plus 3, du is 2x, which there's an x in the numerator. So I'm going to do this because I really get 1 over u. Antiderivative is natural log of u. So I've got this, but then I got to check the chain rule here. If I take the derivative of natural log of x squared plus 3, I get 1 over x squared plus 3 times 2x. Now I don't see a 2 up here, so I need a 1/2 there for the chain rule. Now this one is not so nice. Now I will tell you, you do enough of these and you start to recognize I can see that that one's going to be an inverse tangent, but you might not see it. So we can do the trig sub. I would make x equal, let's see, root 3 tangent u, because tangent squared u plus 1 is secant squared u. Dx is root 3 secant squared u. But watch what happens. So these, I'm just doing this part now. So this would become integral of root 3 secant squared u over 3 tangent squared u plus 1 du. And this, oops, this is a 3, will become 3 times tangent squared plus 1, or 3 secant squared u. So that secant squared would cancel with this, and I'd have root 3 over 3 integral du, which is root 3 over 3 u plus c, which is root 3 over 3, let's see. U is inverse tangent of x over root 3. Let's see. So then my whole answer is negative natural log of x plus 1/2 natural log of x squared plus 3 plus root 3 over 3 inverse tangent of x over root 3, and don't forget the c. So sometimes I have students that memorize 1 over x squared plus 1, you get inverse tangent, and that's fine. I find, for me, I cannot reliably mess around with that 3 and get it to come out. I often put the 3's in the wrong places. So I always just do trig sub with it, knowing that I know I'm going to end up with some kind of inverse tangent, but then I sometimes I can't remember what goes inside the argument of the inverse tangent. So I just do it with trig sub. Okay, so yeah, that's a handful of a problem, and the new thing we introduced here was the quadratic denominator. So let's kind of keep going with our work here and look at another one of these. So this one's already factored for us, that's the good news. Now, there's a couple things you could do here. I'm going to sort of show you an evolution. One would be to do a over x and then x minus 1 cubed. And this is a cubic, so we would have a quadratic. Okay. But sort of looking ahead to the calculus, if you get this second thing, that's not going to have a nice antiderivative, is it? It's going to be really gross. So we can actually be kind of strategic about it and also make sense of some partial fractions. I'm going to say instead of bx squared, since I haven't found b, these are not equivalent, by the way, I'm going to use x minus 1 instead, for reasons that will hopefully become apparent. Why did I change from to x minus 1? So again, this is not the same as this. These values of b, c, and d would come out totally different, and that's okay. Why is this a better sort of generic numerator? It's definitely a quadratic, so I've gone 1 degree less, which is the only requirement. If I do this, I can simplify it. I can split this into 3 fractions, b x minus 1 squared over x minus 1 cubed, which simplifies to b over x minus 1. Well, that would have a nice antiderivative, wouldn't it? And then this middle one would simplify to c over x minus 1 squared. As we'll see later, that's also going to have a nice antiderivative. And then d over x minus 1. So this is actually doing the same rule I showed you in the last problem, which is going 1 degree less. But it turns out that it has this nice rewrite. And if you see that, you can usually go straight to this equivalent rewrite. So this is a method called, if you've got a repeating factor in the denominator, like x minus 1 is a factor 3 times. Rather than writing out a quadratic numerator, take that repeated factor and do it to the first power, to the second power, to the third power, and then you just need constant numerators. So if you have a repeating factor in the denominator, rather than doing it as one fraction, do it however many times it repeats with increasingly higher powers of that repeating factor. All right, let's check it out. Let's see what happens. So Here, my common denominator would be x times x minus 1 cubed. So I'll warn you, this is going to get a little hairy. A times x minus 1 cubed. And then b, I would have to multiply by x and by x minus 1 squared. C, I would have to multiply by x and by x minus 1. And d, I'd have to multiply by x. So with repeating factors, the completion of the partial fractions can actually be sort of horrible. So just prepare yourself for that horribleness, I guess. All right, so, oh boy. All right, nothing for it. Well, actually, I can find two things right away. I could sub in an x equals 1, and a, b, and c go away. Those all are 0 then. So when x equals 1, I have d equals 1 squared plus 1 is 2. So I just found d. The other convenient value I could put in would be a 0. If I put in a 0, b, c, and d are all 0. And so I have negative 1a equals 1, or a is negative 1. So I've already got a and d. That's not so bad then, right? Unfortunately, there is no convenient value that keeps b or c and gets rid of other things, since they have everything in them. So I'm going to have to suck it up and do at least a couple equations for a system. Oh, I'm trying to avoid this, but yeah, I don't think I can. All right, here's what I'm going to do. I'm going to look at the x cubed terms. So a x cubed, right? What I'm trying to really avoid is expanding x minus 1 to the third, because that's yucky. So there's an a x cubed. There is also a bx cubed. And there's no cx cubed and no dx cubed. Well, that's kind of nice, isn't it? So, and there is no x cubed on the right over here, so this would be 0. Well, okay, that's not so bad. If a is negative 1, then b must be, oops, I don't know why I used an arrow. B must be 1. So again, the difficulty here is not actually the calculus at all, it's just all this nasty algebra. All right, so I've got a, b, d. I'm going to get c. I think there's nothing for it. I've got to do the x squared terms, I think. Did I really? Yeah, the x terms aren't going to be any better. Oh, I don't want to. Shoot. All right. All right. What I've been trying to avoid is apparently unavoidable. I expanded x minus 1 cubed using binomial expansion. X squared minus 2x plus 1. C x squared minus x plus dx. All right, so I'm going to do one thing so I can get my c terms. So I'm just going to do the x squared ones. So let's see, I've got negative 3a from there. I have this and this, so this would be plus, minus 2bx squared plus c x squared equals 1. Now I've already got a is negative 1, so negative 3 times negative 1 is 3. B is 1 minus 2 plus c equals 1. Oh, well, that's kind of handy. C is 0. Okay, so I've got A, B, here, I'll highlight these. A, B, C, and D. Okay. All right, let's go up here and change our integral then. So this becomes integral of A was negative 1. Negative 1 over x plus b was 1 over x minus 1. C was 0, so no anything over x minus 1 squared, but d was 2. I really hope I haven't made a mistake on any of these. There we go. Okay, the good news is there's no trig sub needed. Yay! We can actually just find the antiderivative of all of these. Antiderivative of -1 over x is negative natural log absolute value of x. Antiderivative of the next one, another log. And then this one, this is the same as 2 times x minus 1 to the -3rd. So I can just do the power rule. When you do the power rule, you increase the power. So if the power is at -3, increasing that gives us to the -2 power. And then I just got to think about that power. So if I take the derivative of x minus 1 to the -2, I'd have -2. The 2 I want, and the negative I don't. So I think I'll leave this as a minus. My spacing got a little weird, but that's okay. So depending if it was multiple choice or something like that, we might want to combine these two logs. It's unclear. Remember, subtracting logs means you have a quotient inside the logs, and we might want to rewrite this. And there is my final answer. Sorry, the partial fractions got a little messy, but that is in fact how you do it. And again, just to reiterate, I do not usually write this, but this is just sort of my justification for why we can instead just do this with the repeating factors. You can proceed right to this one right here and do it. Okay. All right. Hope you enjoyed these examples. I'll zoom out in case you need to write anything else down. And we'll talk more in class.